In this lecture, we are going to understand the MOS under biasing condition. When we say MOS under bias, we have two choices. Either metal could be a positive or metal could be a negative. When it is a p-type semiconductor, we have three different cases. One with Vg equal to negative. That means negative. Metal is negative. And we break actually the positive condition into two. So when we apply a positive voltage on the metal, we divide it into two, positive small and positive large. Why we do so? Because in small and large the MOS behaves in a different way. Let's understand one by one each and every one. So when Vg is equal to negative, what happens is the body is at actually 0, Vg is negative. So what happens is the electric field direction is upside. Electric field direction is upside, and because of this electric field direction upside, the holes get accumulated near the SiO2 interface. If we wanted to show the same condition in the band diagram, how we can show? We can show by putting the bending upward. Why the bending is upward? You can directly understand this by seeing the electric field. The electric field direction is upward, definitely the band has to bend upside. Now in this condition, how this condition is important as far as the MOSFET is concerned, we need to understand that also. So what is a MOSFET? So we have made a MOSFET structure over here, the schematic diagram over here. So let's say it's a p-type semiconductor. In p-type semiconductor you have two diffusion region, which is N plus and N plus. And this terminal is known as a drain and this terminal is known as a source. What do we want in a MOSFET? We want that by applying a voltage, so in between the MOSFET you have a MOS also. Remember, this is MOS. So this is your metal, this is your oxide, this is your semiconductor. Okay, so what is our purpose? Our purpose is by applying the voltage at the gate, we wanted to control the electrical connection between the source and drain. So you can clearly see that when Vg is less than 0, since in between the source, which is a N plus, and in between the drain, which is also N plus, you have majority of holes. That means there is no electrical connections provided in the accumulation conditions, because this condition is known as a accumulation, where you have accumulations of holes. Okay, so under the accumulation condition, there is no connection between the source and drain. Or you can say when the Vg is less than 0, or you can say the Vg is negative, the gate voltage is negative in case of an MOSFET. Remember, this is when you have source and drain, so this complete as a it's a MOSFET. So this MOS was a P, but this MOSFET is a N channel MOSFET. So in N channel MOSFET, if you apply a Vg which is a negative, it does not provide an electrical connection between source and drain, and hence you can say there is no channel between source and drain, and device is acting as in off condition. Now let's understand the another condition, which is Vg greater than 0. And remember, we are considering a case when Vg is greater than 0 but it is a small. What happens is when Vg is a small, you have a small electric field directed towards the downside. If the electric field is directed towards the downside, the bending has to be done towards the downside. What happens is when you apply a small positive voltage, it repels the holes. It basically repels the hole towards the substrate. ये substrates की तरफ holes को repel करता है, and each holes will leave negatively charged fixed acceptor ions behind. That means you have now the negative charges over here. These are the fixed acceptor ions in the p-type substrate. Okay, so if this is the case, this condition is known as a depletion condition, because under this condition there is no charge carrier below the SiO2 interface. Near the SiO2 interface you don't have any mobile charge carrier. You have charge carrier, but these charge carrier are fixed in nature. These are fixed, they don't contribute into the current, they are fixed. So basically, since you don't have any charge carrier, this condition is known as a depletion condition. So what happens is, if you map this depletion condition onto the MOSFET, what is the kind of a situations we have. So when you apply a VG which is greater than 0 but a small voltage, what happens is you have in between the source and drain you have electrically insulated region. That means there is no electrical connections, there is no, basically just a second, there is no electrical connections between source and drain, because you have in between a highly resistive channel, so the current cannot flow from source to drain in this condition also. So what does it mean? It means under G is greater than 0, when the voltage, the gate voltage is positive but small, no channel exists between the source and drain, no electrical connections exist between the source and drain. So positive small voltage at gate in N MOSFET is actually make the device off. So that means even if you have a VG negative or even if you have a VG 0 but small, in both the condition there is no electrical connections between the source and drain. Now let's consider the third case, which is the VG equal to 0 but it is a large. So when you apply VG which is greater than 0, also large, again the electric field direction in the oxide is towards downside. Why? Because this is positive and this is 0. So definitely the electric field direction will be like this. If the electric field direction will be like this, the bending will be even more than the previous case. If the bending will be more, what is going to happen is, because if you are increasing a positive voltage, it is basically attracting the minority charge carrier which are there in the p-type substrate. So you have now the minority charge carrier over here, you have a layer of minority charge carrier. So if you wanted to depict the similar kind of a situation onto the band diagram, then what happens is the surface potential. So this is the surface potential. This surface potential becomes in the channel region reaches minus 5 fp. So here you have a 5 fp, and let me tell you here. So here you have this, just a second, you have this is minus 5 fp. So that means जो यहाँ पे पी टाइप आपकी वेफर है वो यहाँ पर आपकी एन टाइप वेफर की तरह एक्ट कर रही है, बिकॉज नाउ यू आर वेरी क्लोज टू द कंडक्शन बैंड. सो दैट मीन्स हेयर यू हैव ए लार्ज नंबर ऑफ इलेक्ट्रॉन्स. ओके, इफ यू depict, if you map the similar situation onto the MOSFET, what happens is you have a N plus which is a source region, you have a N plus which is a drain region, and if you apply at the metal or at the gate terminal a gate voltage which is greater than 0 but large, then what happens is you have a electron layer near the SiO2 interface. This channel basically provides an electrical connection between the two N plus region. The value of gate voltage needed to cause the surface inversion is basically called the threshold voltage of the MOSFET. Basically threshold voltage is the voltage where you have a inversion conditions. So if Vg is greater than Vt naught, that means Vg is less than Vt naught, that means there is no channel between the source and drain, and if there is no channel between the source and drain, you don't have any current. If you have a Vg which is greater than Vt naught, there is a channel exist between the source and drain, and there is a current also. So that means just by controlling the gate voltage, at the gate terminal, you can control the electrical connections between the source and drain. Whenever Vg is less than 0 or less than threshold voltage, basically the MOSFET is in off condition, and whenever Vg is basically greater than Vt naught, meaning there is a inversion conditions near the SiO2 interface, the MOSFET or there is a electrical connections between source and drain exist, and the MOSFET called in a on condition. Thank you.